theme of high-speed automation, high-throughput manufacturing, cost-effective manufacturing. It needs to be implemented in different ways for different types of products. So, for example, we've taken the same parallel alignment technology, the same technology that we showed you in the last workstation, where we can perform multiple inputs, outputs, degrees of freedom using the 6 degree of freedom mechanisms you saw. We've taken that same technology and we've built it into other products in our product line. For example, here is a 6 degree of freedom, all piezo positioner. 6 degrees of freedom, extremely high reliability, extremely high lifetime, because piezo devices, piezo flexure mechanisms, there are no wear mechanisms, no particulate generation mechanisms, so it's extremely clean and extremely high resolution as well. So this Piezo Hexapod is part of our nanocube family of positioners. It has these alignment algorithms built in. You can see it running here doing an array alignment. And the interesting thing about this is that even though it is a piezo flexure mechanism, it has very large travels for a piezo flexure mechanism. About 0.5 millimeter of travel. That's more than enough to accommodate the production variances from part to part and fixturing and things of that sort. So this is a highly optimized mechanism for high throughput manufacturing and test of photonic devices. Here, you might want to bring the camera over so that you can see what's going on here. We've taken our fast alignment mechanism, our fast alignment technology, and we've built it into linear motor stages, compact, very cost-effective linear motor stages that are able to do the alignment technologies as I've described it. And these algorithms are all built into the controller. That's one reason why they're so fast. So that means we can control it with a simple HMI like this, so that in a production application, the robustness of a controller-based architecture is one of the benefits for an application of this sort. In many materials sciences, life sciences, applications, and biomedicine, and things of that sort, it's necessary to perform optical metrology and imaging of specimens, samples. For example, you may have a well plate which can contain biological samples, and each of these wells needs to be scanned and inspected and measured, perhaps for optical characteristics and things of that sort. So what we've done is we've built a very flexible platform that you can build an application around. It's part of our PI Nano approach of modular, coarse and fine, and structural architectures for building generic applications. So in this case, you can see many examples of configurations built on the same theme here, the same kind of mechanisms. And so people are building entire tools out of this. You can see in the open architecture underneath, you have a very flexible, very rigid, very high precision architecture for building optical metrology that combines optical instrumentation with very high performance, coarse fine positioning of your samples. Here's another example of a PI Nano coarse fine system that customers can use to build a microscopy-based system for optical metrology, automated optical metrology of large samples. Well plates, again, are a very common example, but it can be any number of other things, ranging from microscope slides to samples of materials and things of that sort. The optical metrology is something that the customer would address using whatever instrumentation they may need for their particular metrology. These systems are available with multiple degrees of freedom, with additional optional piezo autofocus, very fast piezo autofocus for optical imaging applications, to be joysticks for manual positioning, as well as the automated functionality. Now, we have many applications in photonics for beam steering, fast beam steering. For example, writing patterns on a wafer or a substrate of some sort, or writing a photomask, or free space optical communications, where you basically do the same thing you do with optical fiber communications. Light goes in one side, comes out the other. You could convert data and information from one side to the other. We'll take the fiber away, and that's what free space optical communications is. It is actually a very important field for photonics in general, because you see applications, companies like SpaceX and Amazon's Project Kuiper, which are using arrays of low Earth orbit satellites, beaming laser beams between each other so that you can get internet connectivity from any point on the Earth's surface to any other point on the Earth's surface with very low latencies, because these satellites are only a couple hundred miles up. So that requires beam steering to lock the communications between satellites and to enable the satellite-to-ground communications as well. So that sort of mirror mount is something that we make in large quantities using piezo technology and also voice coil technology, depending on the application. So here you can see an application where we are making rapid patterns, very repeatable, using one of these. In this case, it's a voice coil-driven mount. So to our customers and colleagues in the photonics industry, I'd like to summarize by saying thank you. Thank you for working with us, for being our customers and colleagues over the past 51 years of PI's existence. As we confront the challenges that the industry's success is posing for us, please think of us. Please give us a call. We are a global company. We have applications engineers and specialists around the world who can help you with your applications, whether it's on Earth or in orbit, in a fab, in a laboratory. Give us a call.